In mathematics, a set is a collection of distinct objects, considered as an object in its own right. For example, the numbers chapter 2, 4, and 6 are distinct objects when considered separately, but when they are considered collectively they form a single set of size 3, written 2, 4, 6. Sets are one of the most fundamental concepts in mathematics. Developed at the end of the 19th century, set theory is now a ubiquitous part of mathematics, and can be used as a foundation from which nearly all of mathematics can be derived. In mathematics education, elementary topics such as Venn diagrams are taught at a young age, while more advanced concepts are taught as part of a university degree. The German word Menge, rendered as set in English, was coined by Bernard Bolzano in his work The Paradoxes of the Infinite. Definition: a set is a well-defined collection of distinct objects. The objects that make up a set can be anything: numbers, people, letters of the alphabet, other sets, and so on. Georg Cantor, the founder of set theory, gave the following definition of a set at the beginning of his Betrachtung zur Begründung der transfiniten Mengenlehre. A set is a gathering together into a whole of definite, distinct objects of our perception, Anschauung, or of our thought, which are called elements of the set. Sets are conventionally denoted with capital letters. Sets A and B are equal if and only if they have precisely the same elements. Cantor's definition turned out to be inadequate for formal mathematics. Instead, the notion of a set is taken as an undefined primitive in axiomatic set theory, and its properties are defined by the Zermelo-Fraenkel axioms. The most basic properties are that a set has elements, and that two sets are equal if and only if every element of each set is an element of the other. Describing sets. There are two ways of describing, or specifying the members of, a set. One way is by intentional definition, using a rule or semantic description. A is the set whose members are the first four positive integers. B is the set of colors of the French flag. The second way is by extension, that is, listing each member of the set. An extensional definition is denoted by enclosing the list of members in curly brackets. C equals 4, 2, 1, 3. D equals blue, white, red. One often has the choice of specifying a set either intentionally or extensionally. In the examples above, for instance, A equals C and B equals D. There are two important points to note about sets. First, a set can have two or more members which are identical, for example, 11, 6, 6. However, we say that two sets which differ only in that one has duplicate members are in fact exactly identical. Hence, the set 11, 6, 6 is exactly identical to the set 11, 6. The second important point is that the order in which the elements of a set are listed is irrelevant. We can illustrate these two important points with an example. 6, 11 equals 11, 6 equals 11, 6, 6, 11. For sets with many elements, the enumeration of members can be abbreviated. For instance, the set of the first 1,000 positive integers may be specified extensionally as 1, 2, 3, 1,000, where the ellipsis indicates that the list continues in the obvious way. Ellipses may also be used where sets have infinitely many members. Thus, the set of positive even numbers can be written as 2, 4, 6, 8. The notation with braces may also be used in an intentional specification of a set. In this usage, the braces have the meaning, the set of all. So, E equals playing card suits is the set whose four members are heart, and a more general form of this is set builder notation, through which, for instance, the set F of the 20 smallest integers that are 4 less than perfect squares can be denoted F equals n2 minus 4. N is an integer, and 0 and 19. In this notation, the colon means such that, and the description can be interpreted as F is the set of all numbers of the form n2 minus 4, such that n is a whole number in the range from 0 to 19 inclusive. Sometimes the vertical bar is used instead of the colon. Membership. If B is a set and X is one of the objects of B, this is denoted XB, and is read as X belongs to B, or X is an element of B. If Y is not a member of B, then this is written as YB, and is read as Y does not belong to B. For example, with respect to the sets A equals 1, 2, 3, 4, B equals blue, white, red, and F equals n2-4, n is an integer, and 0 and 19, defined above, for A and 12F but 9F and green B. Subsets. If every member of set A is also a member of set B, then A is said to be a subset of B, written AB. Equivalently, we can write BA, read as B is a superset of A, B includes A, or B contains A. The relationship between sets established by is called inclusion or containment. If A is a subset of, but not equal to, B, then A is called a proper subset of B, written AB or BA. Note that the expressions AB and BA are used differently by different authors. Some authors use them to mean the same as AB, whereas others use them to mean the same as AB. Example: the set of all men is a proper subset of the set of all people. 1, 3, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The empty set is a subset of every set, and every set is a subset of itself. A, an obvious but useful identity, which can often be used to show that two seemingly different sets are equal. A equals B if and only if AB and BA. A partition of a set S is a set of non-empty subsets of S such that every element X in S is in exactly one of these subsets. Power sets. The power set of a set S is the set of all subsets of S. Note that the power set contains S itself and the empty set because these are both subsets of S. For example, the power set of the set 1, 2, 3 is 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. The power set of a set S is usually written as P. The power set of a finite set with n elements has 2n elements. This relationship is one of the reasons for the terminology power set. For example, the set 1, 2, 3 contains 3 elements, and the power set shown above contains 23 equals 8 elements. The power set of an infinite set is always uncountable. Moreover, the power set of a set is always strictly bigger than the original set in the sense that there is no way to pair every element of S with exactly one element of P. Every partition of a set S is a subset of the power set of S. Cardinality. The cardinality S of a set S is the number of members of S. For example, if B equals blue, white, red, B equals 3. There is a unique set with no members and 0 cardinality, which is called the empty set and is denoted by the symbol. For example, the set of all three-sided squares has 0 members and thus is the empty set. Though it may seem trivial, the empty set, like the number 0, is important in mathematics. Indeed, the existence of this set is one of the fundamental concepts of axiomatic set theory. Some sets have infinite cardinality. The set n of natural numbers, for instance, is infinite. Some infinite cardinalities are greater than others. For instance, the set of real numbers has greater cardinality than the set of natural numbers. However, it can be shown that the cardinality of a straight line is the same as the cardinality of any segment of that line, of the entire plane, and indeed of any finite-dimensional Euclidean space. Special sets. There are some sets that hold great mathematical importance and are referred to with such regularity that they have acquired special names and notational conventions to identify them. One of these is the empty set, denoted or. Another is the unit set X, which contains exactly one element, namely X. Many of these sets are represented using blackboard bold or bold typeface. Special sets of numbers include P-or, denoting the set of all primes. P equals 2, 3, 5, 7, 11, 13, 17. N-or, denoting the set of all natural numbers. N equals 1, 2, 3. Z or Z, denoting the set of all integers. Z equals -2, -1, 0, 1, 2. Q or, denoting the set of all rational numbers. Q equals A, B, Z, B0. For example, 1/4 Q and 11/6 Q. All integers are in this set since every integer can be expressed as the fraction of 1. R or, denoting the set of all real numbers. This set includes all rational numbers, together with all irrational numbers. C or, denoting the set of all complex numbers. C equals A plus by A, B, R. For example, 1 plus 2 IC. H or, denoting the set of all quaternions. H equals A plus by plus CJ plus DK. A, B, C, DR. For example, 1 plus I plus 2J minus KH. Positive and negative sets are denoted by a superscript, or plus. For example, plus represents the set of positive rational numbers. Each of the above sets of numbers has an infinite number of elements, and each can be considered to be a proper subset of the sets listed below it. The primes are used less frequently than the others outside of number theory and related fields. Basic operations. There are several fundamental operations for constructing new sets from given sets. Unions. Two sets can be added together. The union of A and B, denoted by AB, is the set of all things that are members of either A or B. Examples: 1, 2, 1, 2 equals 1, 2. 1, 2, 2, 3 equals 1, 2, 3. 1, 2, 3, 3, 4, 5 equals 1, 2, 3, 4, 5. Some basic properties of unions. A B equals BA, A equals C, A equals A equals A, a B if and only if AB equals B. Intersections. A new set can also be constructed by determining which members two sets have in common. The intersection of A and B, denoted by AB, is the set of all things that are members of both A and B. If AB equals, then A and B are said to be disjoint. Examples: 1, 2, 1, 2 equals 1, 2. 1, 2, 2, 3 equals 2. Some basic properties of intersections. A B equals BA, A equals C, a BA, A equals A equals a B if and only if AB equals A. Complements. Two sets can also be subtracted. The relative complement of B in A, denoted by A, B, is the set of all elements that are members of A but not members of B. Note that it is valid to subtract members of a set that are not in the set, such as removing the element green from the set 1, 2, 3. Doing so has no effect. In certain settings, all sets under discussion are considered to be subsets of a given universal set U. In such cases, U A is called the absolute complement or simply complement of A, and is denoted by A. Examples: 1, 2, 1, 2 equals 1, 2, 3, 4, 1, 3 equals 2, 4. If U is the set of integers, E is the set of even integers, and O is the set of odd integers, then U E equals O. Some basic properties of complements. A, B, B, A for AB, A equals U, A equals A equals U equals and equals U, A, B equals AB. An extension of the complement is the symmetric difference, defined for sets A, B as, for example, the symmetric difference of 7, 8, 9, 10, and 9, 10, 11, 12 is the set 7, 8, 11, 12. Cartesian product. A new set can be constructed by associating every element of one set with every element of another set. The Cartesian product of two sets A and B, denoted by A times B, is the set of all ordered pairs such that A is a member of A and B is a member of B. Examples: 1, 2 times red, white equals 1, 2 times red, white, green equals 1, 2 times 1, 2 equals Some basic properties of Cartesian products: A times equals, A times equals, times C equals. Let A and B be finite sets. Then, A times B equals B times A equals A times B. For example, A, B, C times D, E, F equals. Applications. Set theory is seen as the foundation from which virtually all of mathematics can be derived. For example, structures in abstract algebra, such as groups, fields and rings, are sets closed under one or more operations. One of the main applications of naive set theory is constructing relations. A relation from a domain A to a codomain B is a subset of the Cartesian product A times B. Given this concept, we are quick to see that the set F of all ordered pairs, where X is real, is quite familiar. It has a domain set R and a codomain set that is also R, because the set of all squares is subset of the set of all reals. If placed in functional notation, this relation becomes F equals X2. The reason these two are equivalent is for any given value, y that the function is defined for, its corresponding ordered pair is a member of the set F. Axiomatic set theory. Although initially naive set theory, which defines a set merely as any well-defined collection, was well accepted, it soon ran into several obstacles. It was found that this definition spawned several paradoxes, most notably Russell's paradox. It shows that the set of all sets that do not contain themselves, i.e., the set X is a set and XX does not exist. Cantor's paradox. It shows that the set of all sets cannot exist. The reason is that the phrase well-defined is not very well defined. It was important onto free set theory of these paradoxes because nearly all of mathematics was being redefined in terms of set theory. In an attempt to avoid these paradoxes, set theory was axiomatized based on first-order logic, and thus axiomatic set theory was born. For most purposes, however, naive set theory is still useful. Principle of inclusion and exclusion. This principle gives us the cardinality of the union of sets. De Morgan's law. De Morgan stated two laws about sets. If A and B are any two sets, then equals A, B. The complement of A union B equals the complement of A intersected with the complement of B equals A, B. The complement of A intersected with B is equal to the complement of A union to the complement of B.